Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we'll discuss about data preprocessing. The real-world training data is hardly perfect. It is usually not clean and it has got many issues such as missing values for certain features, features on different scales, non-numeric attributes, etc. Often there is a need to preprocess the data to make it amenable for training the model. sklearn provides a rich set of transformers for this job. However, we have to make sure that we apply the same set of transformations to both training, test as well as on the evaluation set. And this is where most of the real world pipeline sometimes, if they do not take enough care, it may cause some kind of a problem. Fortunately, sklearn provides a pipeline class for making it easier to chain multiple transformers together. And pipeline also ensures that we apply these transformations uniformly across training, eval, and test sets. So usually once you get the training data, the first job is to explore the data and list down the preprocessing steps that are needed. Typical problems with training data include missing values in the features, numerical features are often not on the same scale, categorical attributes needs to be represented with sensible numerical representation, there are sometimes too many features and not all features are relevant for the learning problem and hence we need to reduce them. Sometimes we are faced with non-numerical data like images and text and we want to extract features from those non-numerical data. So sklearn provides a library of transformers for data preprocessing. There are a set of transformers for data cleaning. They come in the module sklearn.preprocessing and this sklearn.preprocessing module has facility for standardization, missing value imputation, feature scaling, etc. Then we have feature extractors. sklearn.feature_extraction module has bunch of feature extractors to extract features from different data types. Then we have feature reduction. sklearn.decomposition module has got bunch of feature reduction algorithms implemented. One of them is PCA that we will be discussing in this module. And then there are methods for feature expansion that we do especially in kernel methods, and we will study this later once we study support vector machines. Each transformer class has the following methods. The fit method learns model parameters from a training set. Transform method applies a learned transformation to the new data. And alternatively, there is fit_transform method that performs function of both fit and transform. It is more convenient and efficient to use. Let's understand what fit does. Let's say we want to scale the features using z-score. While applying the z-score, we need mean and standard deviation for the feature. And the fit method learns the mean and standard deviation for the features from the training set. It also stores these features and these features are used, these parameters are used in the transform method for transforming the data set from the original set to the transform set. So in case of z-score, the mean and the standard deviation that is learned from the training set is used to transform each feature to its z-score using this learned mean and standard deviation. Let's look at the first part, which is feature extraction. sklearn.feature_extraction module has useful APIs to extract features from the data. There are a couple of them which are interesting to us. The first one is DictionaryVectorizer or DictVectorizer, and second one is FeatureHasher. Let's study these APIs one by one. The dictionary vectorizer converts list of mappings of feature names and feature value into a matrix. Let's take a concrete example. Let's say this is the original data, which is in form of a data frame. Data frame has got two columns. One is age and second is height. And here we have four rows or four samples. The first one has age 4 and height of 96. Second one has age 1 and height of 73.9, and so on. When we apply the dict vectorizer, so we'll have to first initialize, or we'll have to first instantiate the dict vectorizer object, and we have to call, since it's a transformer, it has got fit_transform method. So that's the beauty of sklearn APIs, right? I mean, we studied the design principles of sklearn API, and these APIs are uniform. Once we know that this is a transformer, we can apply fit_transform method. So we instantiate the object, we call fit_transform method on it, and we pass the data as an argument. So this particular data will be transformed by the dictionary vectorizer into a matrix. So this gets transformed specifically into feature matrix. It has got two rows, it has got two columns. The first column corresponds to the age and the second column corresponds to height. And it has got four rows corresponding to the four samples that were there in the original dataset. So you can see that the first sample has got age of 4 and height of 96. The second sample has got age of 1 and height of 73.9, and so on. So this is how dictionary vectorizer works. If you have data present in form of a dictionary or in form of a data frame, dictionary vectorizer converts that into the feature matrix. The second API of our interest is FeatureHasher. FeatureHasher is a high-speed, low-memory vectorizer. It uses feature hashing technique. So here, instead of building a hash table of features, it applies a hash function to the features to determine their column index in the sample matrix directly. This of course results in increased speed and reduced memory usage because now we are not building any kind of hash table. However, there is a cost that we pay, and that cost is the inspectability. We are not able to inspect the features because hasher does not remember what was the original input, and it does not have inverse_transform method to convert the transform feature back to its original form. So that's the cost we pay, but it is extremely fast and efficient to use, especially when we have a very large number of features. So FeatureHasher is typically used in cases like text classification, where we have a very high dimensional feature vectors. And the FeatureHasher outputs a sparse matrix, which is in form of scipy.sparse. We also have sometimes non-numerical data like images and text, and sklearn provides specialized APIs for extracting features from such kind of data sets. In order to extract features from images, sklearn has sklearn.feature_extraction.image class, and sklearn also has a corresponding class for extracting features from text. We will not be covering these two modules in detail in this course because they are very, very specialized, but we have provided links here in the sklearn user guide for you to study these topics further. Now that we have extracted the features, the next task is cleaning up the data. Let's look at the first cleanup operation, which is handling missing values. So we had discussed this in the in the first week when we were learning ML end-to-end pipeline, we said that missing values occur due to errors in data capture, and these errors could be because of sensor malfunctioning, measurement error. There could be some human components also involved in having the missing values. Unfortunately, many machine learning algorithms do not work with missing data, and they need all features to be present. Discarding records that contains missing value is not an option, because when you discard the records, we are throwing away precious training data. Hence, we need a mechanism to handle these missing values. So basically, we want mechanism where we can take these rows with missing features and and fill it up using certain methods. So a SimpleImputer module provides functionality to fill missing values in the dataset. There are a couple of classes implemented in this module. One is SimpleImputer and second is KNNImputer. These two imputers will help us to fill up the missing values. And there is missing indicator class that provides indicators for missing values. This will be very useful if you want to later examine the data and also find out how the classifier or regressor's performance is on these kind of missing features. Let's look at the SimpleImputer class. It fills up missing values with one of the following strategies. Now the idea is that we have a feature, and in that particular feature there are certain samples that are missing. So we are going to handle these missing values, let's say feature by feature, and in one feature, let's say there are a few samples that are missing. Then we need to basically come up with a sensible value for those missing values. So we can either use the mean of that particular feature, or we can use median value, we might use most frequent value, or we can replace missing value with some kind of with some constant. So these are the strategies that will be used in SimpleImputer. Let's take a concrete example. Here we have 4 samples and 2 features. So we have feature matrix X with shape 4, 2. So here in the first feature there is one missing value, and in second feature there is also one missing value. Here the missing value is present in the second sample, and in the second column the missing value is present in the third sample. Now what we do is we apply SimpleImputer on it with strategy mean, and this is how we instantiate the SimpleImputer object by specifying the strategy for filling up the missing values. Then we simply call the fit transform method on this particular feature matrix. So you can see that X, which is our original feature matrix, is the argument to fit_transform method. And we get a transform feature matrix with value 6, which is added, which is replacing the nan in the second sample, and in the third sample value 5 replaces the nan or the missing values. Let's see how these values are computed. So since we are using mean strategy for imputation, the mean of the first column of the first feature is basically 6, and you know how to calculate mean, but for your convenience we have shown it. We have shown the explicit computation of the mean over here. So while calculating mean, we ignore the value which is missing, and we calculate mean with the other values that are present. So in this case the mean is 6, and that value is replaced, that value replaces the nan or the missing value. In the second column the mean is 5, and hence we fill up this particular missing value with the mean, which is 5. So KNNImputer is another class that handles the missing values, that fills up the missing values. It uses k-nearest neighbor approach for filling the missing values. Here what we do is we calculate, so missing value is there for a specific example. We calculate the n nearest neighbor for this particular example, and then we fill up the missing values of an attribute in that example with the mean value of the same attributes of its nearest neighbors. And the nearest neighbors are decided based on Euclidean distance. Let's look at example of KNNImputer. So let's say we have the following feature matrix. It has got 4 samples and 3 features. There are 2 missing values. There is a missing value in the first sample and another missing value in the third sample. Now we'll fill up these missing values with KNNImputers. So this is the original feature matrix, and let's look at the missing value filling for the first sample, and the first sample is 1, 2 and nan, right? So what we'll do is we'll calculate the distance of this first sample with other samples, because the key step here is to find out the nearest neighbor of the sample containing the missing value. Let's look at the nearest neighbor computation. So first we calculate the distance between this particular sample with, let's say, the second sample with using the Euclidean distance formula. So since the third value is nan, we do not consider it for the distance computation. So you know the Euclidean formula is square root of x, the feature x1 of the first example minus feature x1 of the second example, and we square up the difference plus the difference between the second features of these 2 examples, and we square up that difference and we get the value of 2.82. Next we calculate the distance between the first sample and the third sample. So we'll be doing it, we will be calculating distance of first sample with every other sample in the data set. Here there is nan, so we do not consider that, so we only have the second feature to consider for calculating the distance, and it is 4. In the same way we calculate distance with the last example, and that comes out to be 9.21. So if you want to use, let's say, 2 nearest neighbor, the second and the third samples are 2 nearest neighbors for the first sample or for the first row. So now what we'll do is we'll fill up this particular missing value using, let's say, a mean strategy. So we calculate the mean of this particular feature based on these 2 nearest neighbors. So in this case we just consider these 2 values because these are 2 nearest neighbors, and we get the value of 4. So here 2 is the number of nearest neighbor, 3 and 5 are the value of the third feature where we have a missing value in the first example. So we calculate mean of the values of this particular third feature for these 2 examples, and it comes out to be 4. So we fill up this particular missing value with 4. So we get value 1, 2 and 4 after transformation. So in this way we can fill up the missing values with KNNImputer. So let's look at the syntax for KNNImputer. We instantiate KNNImputer object by specifying number of nearest neighbors and the weight that we want to give to the nearest neighbor. Here we give uniform weight. So we are basically weighing each neighbors uniformly. And by default the strategy is mean. We can change it to other values. And here, and then we call fit underscore transform. Again, notice it's fit underscore transform, KNNImputer is also a transformer. Hence, it implements fit underscore transform, and then we pass the original feature matrix and we get a transform feature matrix like this. We have already seen how this 4 was computed, so you can also see how this 5.5 is computed by doing the same computation that we did in the previous slide. It is always useful to indicate the presence of missing values in the dataset, and missing indicator helps us get those indications. Missing indicator returns a binary matrix where true values corresponds to missing entries in the original dataset.